Okay, I'll just do a quick recap since we're recording. All right, so the idea is um, that we have there's a particular interpretation of trace monoidal categories that, as Abramsky says, has a particle-like view.
So you're not sharing the screen if you.
Yeah, yeah. I'm just gonna introduce it. So here's a picture that is commonly associated with that particle-like view. So if you've got some morphism that it's effectively from X to Y, it's really from X tensor U to Y tensor U. And then we use the U as an accumulator in a recursion. That's really what's going on. So then the trace is going to turn this F into an F from X to Y. And the way we can think about it is we can think about it in terms of this like a sort of a standard recursion that you might see in a Scala function. If a particle or an element of a data structure comes in, and if it's of our base case, then it just comes straight out the Y side. We apply our function to the base case and go straight out. If it's of a more complicated situation, so it's a list we have to decompose or a tree we have to decompose, something like that. Then we come out. Then we go down the U path. We go out the U side and come back in the U side, and we check to see, have we simplified it enough? In which case we can apply our function and go out the Y side. Otherwise, we go out the U side, again decomposing further our data structure. Come back in. Have we decomposed it enough? Etc. And that's represented by this function, this kind of formula here. Although this formula is specific to partial injective functions and sets, it's the same function for lots and lots of examples in this particular paper. So again, the idea is I can think of this plus as an either. I mean, there's another way to think about it, which is the contribution of that piece. But I can think of it as an either, right? So either I come straight out, or I go in via X, I come out via U, I go around the U loop n times, and then I go out the U the final time and come out the Y. So that's how the algebra lines up with the picture. And what I was saying is that, in the ladle construction, we might have notions of computation that don't look like the categorical view. But the ladle provides a kind of mediation. So processes don't necessarily look like morphisms from X to Y. It's not immediately obvious how they're morphisms from X to Y. But what ladle provides is this mediation via this rely guarantee point of view. So this arrow here, this rely guarantee arrow, gives us that view of our computation. But it's much more generic. What it's saying is that this is all the computations U, such that you can decompose U into an application of the red X to some whole, right? So basically, U is it's like a lambda, right? So we're forming the left-hand side of a rewrite, and then whenever we plug the hole with something of type tau, so that's the left-hand side of the arrow. Whenever we plug the hole with something of type tau, and the rewrite applies in one step, then what we get is of type tau prime. So it's basically saying there's no way to plug the hole with a thing of type tau that doesn't get you a thing of type tau prime. So I can rely on things of type tau to give me things of type tau prime. And that's the way you read this. We can rely on things of type tau to guarantee things of type tau prime. That's the rely guarantee interpretation. And now what we can see here when we look at the type system is that they're basically, you can form an inductive proof with respect to how arrows are constructed. So arrows are there are only two kinds of arrows, right? There's atomic arrows, in which case we're done, or there's composite arrows, right? So the atomic arrows are the f of x to y components, and then the composite arrows, they potentially have this interior computation going on, right? So if the arrow inside is really going from A to B to C to D to E, right? And we would just want to look at the A to E behavior. We have to worry about the internal behavior. So if I put in parallel composition two processes that can interact, right? Two row processes that can interact, I have to worry about whether or not that interaction can go awry, in the sense of it can take up infinite amount of resources, or it can compute forever, right? So those are the things that I have to worry about. And so what the type system is doing is it's saying, well, at the seams, we sprinkle in these evaluation contexts, which you can think of as providing a kind of barrier for the computation, but also providing just enough gas for the subcomponents to do their job and nothing more. So that's an example here. Similarly, an example, the place where it's interesting is, so if I have an arrow type here, and I have the thing that can fill the hole, then I'm getting the thing that comes out, right? And that's really the sort of paradigmatic example of what I'm talking about. I have just enough juice to get the thing that comes out and no more. So I can't go around the loop forever. That's the idea. And so one way to think about this aspect of the ladle construction is that it's giving a kind of free, the input is some model of computation which is not necessarily traced. And the output is a model of computation that's kind of freely traced. And so what we've found a way to insert a trace, and the natural place to insert the trace is, of course, on the left-hand side of every red X, right? So for example, if we are looking at the row combinators paper, we're inserting the evaluation context machinery at the left-hand side of all the rewrite rules. That's what's going on. Does that make sense?
Yeah. Can you maybe just say, I'm not completely sure that I understand how you do this on the left-hand side.
Yeah.
Or what?
So that's what the arrow construction is all about. So if we go back up here, right? So K is the gadget that we use to form the left-hand side of an arrow. So in the case of lambda, that's K is application. In the case of a pi or row, K is par. Okay, and And so what we're saying is the arrow type is all of the terms that look like the formation of the left-hand side where one of the components has been left out. So, for example, in the case of the row combinators, it would be like this one, K blank, little k blank.
Yeah,
Okay,
yeah, yeah. So
and then
instead,
go ahead.
instead of just thinking directly of some specific reduction, like in lambda calculus, k is like parametric. So we're not saying exactly what it is, right?
Yeah, that's right. We're leaving. We
Okay.
want this to work for every
Yeah.
model of computation.
Yeah.
Yeah, that's the idea. So, so you hand us a collection of rewrite rules, and the rewrite rules have. So there are two things that we have to have. The left hand side of all the rewrite rules has to be unique in the sense that you don't have k with the m going to a 0 and k with the m also going to some p, right? And the left hand sides have to be unique in all the rewrite rules, which does not mean that we can't handle races. It's a uniqueness that's one level up from the term level, right? These are schema, not instances. And then the other thing is that the model side has to be the free model. So the model can't have in it some sneaky rewrites that aren't represented in the syntactic presentation. So that's another piece of the puzzle. But as long as those two conditions hold, then ladle works. So that means it works for lambda, it works for pi, it works for rho, it works for all the the usual suspects. So that's the idea there, and then with the type system, what we're doing is we're insisting that you can't apply your arrows, right? So if I have an arrow, then I can plug arrows together, right? So that's the let's see, here it is. If I have an arrow and I have a thing that fits the left-hand side of the arrow, then I can't make that wiring. Right? I can't plug the thing into the hole in the box without putting an evaluation context around it. So you can map this R, the evaluation context, directly onto, if you want to visualize it, the R is directly the box. This is your evaluation context. That's the idea.
Yeah, this makes sense.
Cool. Cool.
Yeah, well, I was struggling to understand what is the K, and I think now it's much more clear.
Oh, good. Yeah. Well, thanks for asking the question. So that's so I'm hoping that as we flesh out the categorical semantics, we can make this free trace idea explicit in the paper. We might have to modularize things a little bit, right? The paper is already long, and we still have to put in the expository text. I mean, all we've got is just the math, so we're going to have to add a bunch of English that explains the math, and that's going to make the paper even longer. And so then if we have to also include sort of the discussion of what a trace is, and you can see so to talk about traces, it's quite a bit of work. Here, let's see if I can find just the axiom presentation. Hang on. Where is it? Okay. Here we are. So in general, we would have to do this and motivate it. Yeah, so that will require quite a bit of unpacking, because we'll have to unpack what a symmetric monoidal category is, and then talk about these conditions, and then you know, kind of motivate these conditions. Yeah. So this is again the same idea as thinking of the trace as feedback along the U. Right. So that's the general idea.
And why is called symmetric?
Symmetric monoidal is that you've got a morphism from X tensor Y to Y tensor X, called a braiding, or the symmetry. Yeah. So you can see this is the general shape. I've got the Hom set from X tensor U to Y tensor U, and I shrink it down to just X to Y. So I've got some morphism F that's running this way, and then I shrink it down. So in order to make this construction work, right, we're going to have to talk about, you know, what is the U that we're tensoring with. So that'll be the part that makes this the connection very explicit. So it's essentially, you know, it's all of the stuff that the evaluation context provides. That's the type of U, right? So it's all of the stuff that the evaluation context is potentially hiding. That's implicitly, you know, I've got a tau tensor some stuff here and a tau prime tensor some stuff here, and which represents all of the potential extraneous behavior that this could do. So that's what's going on.
So you're saying that in K, T, comma U, inside there can be some other U from Abramsky's paper, which is not visible here.
That's right. That's right. The way we'll connect it, and the reason it is even possible to connect it is because we have these par constructors. Now, this is not par in the sense of you know, parallel composition, but par in the sense of linear logic. So we're able to pair up gadgets. And then and there are essentially two ways to pair things up. You can pair things up, and I've talked about this before. You can pair things up so that when you unpack them, they're in series, and you can pair things up so that when you unpack them, they're in parallel. So here we have these two things come in, you know, they're come in duals, right? So if gamma is what I need to establish that T is of type tau, and delta is what I need to establish that U is of type tau prime, then I can put them together in a K. So think about it as You know, I could apply them, or I could put them in parallel composition. But here, I'm denying them the R that's necessary to run. And since they don't have the R that's necessary to run, then the K acts as a pairing operator, right? It's it's just, you know, placing them syntactically in a context where I've got the two pieces, but they can't run. They're frozen. They're stuck. Um,
This is like deferred execution, like.
Yep, that's exactly right. And so now you can see the connection to phlogiston, right? Because what phlogiston does is it defers your execution. If you don't have phlogiston, you can't keep running. You can only run in the presence of phlogiston, and that's what this R is doing, right? But the thing is that if I can't extract these two components, then they're stuck inside that pairing. I don't know how to get them out. I don't even know which one is T and which one is U necessarily. If it's symmetric, I don't know which one is which. So we introduce another syntactic gadget, which is the pairing, which is literally a kind of pairing that's going to be used with this pair. And essentially what happens is that this, when we do a cut, so we're now doing a composition, and this composed with this is going to wire. You can either wire T to T. Oh, if you look at it here, right? I've got they're flipped around, right? I've got the upside down ampersand, which is called par, on the left hand side, and a tensor on the right hand side. So I can do a T1 with a T3 and a T2 with a T4. That's this one. Or I can go the other way, right? So again, I'm still pairing. It's the same operation, right? So I get the same term, but the programmer is declaring an intent to use. And over here is the unpacking terms, right? And so when they're put together, which is down here, where is it? This one, yes. Then they go not T1 to T3, they go T1 to T2, right? So this one to this one, and T3 to T4, and then we wire up the results. So those are the only two ways you can go, right? You can either, when you put things together like this, you can either go, you know, across or in series, right? So it's literally just like electrical circuits. It's just like these kinds of wiring diagrams up here, right? So that's why they're called. They're given the names that they're given. So this is basically parallel and series. So now, well, the reason I was mentioning this is we have two kinds of tensors, actually. These are both tensors, right? And these tensors, if K is symmetric, then it's symmetric on the nose, right? If it's not, then you have to, if you twist these, you have to know how to twist these. And that's very easy, right? Because they're not allowed to interact. So twisting them does nothing in terms of the effect on the computation, because we're only going to pull them out using these guys, right? So that's what makes this thing the kind of category where we can affect our trace. We can interpret this operator here in terms of this type operator here, which is implemented in terms of the term structure here. So
when you construct the term KTU, you necessarily do you need to specify the type, or you can say I have some more general type and I will decide later how to deconstruct?
No, this algorithm is saying how to make the type at the time you make the term.
Mm.
In fact, the whole point of this presentation is that it's making the
Yes.
type as you build the terms.
Mm. I see.
But
So later,
you can also run it backwards, right? You can say, if I have a term of this type, is that valid? Is that a real typing, right? And then you run it backwards and say, well, it would be valid if I could establish this and I could establish this. And then, this is valid if I can establish, this one is this one. So I'd have to get this precondition, and this one is that one. So I'd have to get this precondition, right? And so you can run the proof tree. And if the proof, if running it backwards terminates in axioms, like this axiom here, then
this is
or
like a type inference
yeah.
because
Well, no,
from the term.
it's type checking. It's not type inference. It's type checking.
Okay.
Yeah. So you can either running it forwards is like type inference, but you need specific. But type inference is tricky, right? Because as I said, you have to have this declares programmer input intent, right? Right. Right. So someone has to choose some agent because the left-hand side is not distinguished, right? So you have to say how you're doing it.
I was thinking if I use a par as a term constructor to deconstruct, I was thinking that inference can infer which type of K I'm using as an input.
If you have a cut, you can do that, right? Because
Yeah.
you see how it was wired up.
Yeah.
But
Okay.
if you don't, right? If you just have one side of this, it's hard to know without the type.
Yeah.
Yeah.
So if I'm constructing K, I can just say this is like this is the type, and I'm really the term is the same, but with the type I can decide how this will be wired up.
Yeah.
Nice.
So anyway, so that's what I wanted to mention today. So just a little bit more of the puzzle. So what Ladle does then is it you hand us a notion of computation. We hand you back a type system, and that type system is directly connected to a free geometry of interaction interpretation of the notion of computation that you handed us. So we're sort of freely generating a GOI situation on top of the notion of computation that has been handed us. And it uses this idea of gas or an evaluation context to provide that. And it works, it should work. I mean, an interesting test for Ladle would be the ambient calculus. Because and it should work, right? Because so far we've done this in terms of combinatory algebras where there's no substitution, and the ambient calculus is more combinatory in that sense that the in, out, and dissolve operations of the I think they call them open, in, out, and open, but it's essentially rupturing the membrane, rupturing the ambient. So those operations are more combinatory. They're whole tree rewrite. So we should be able to apply this construction to the ambient calculus without a lot of mess and fuss. So that would be quite interesting, right? We're giving a fairly broad range of computational models, these types. And the other point is, of course, that it then places these computational models in it gives an impedance matching gadget between the computational model and the category theoretic view. Right. So we're getting a view of like that's more like boxes and wires glued together. Um, so which has been tricky for the concurrent calculi, right? That a compelling account of a categorical view has not been so easily forthcoming, right? Milner spent the last uh, decade of his life trying to come up with a compelling account, right? One that covered the ambient view and the pi view and other views like that. And it hasn't been super clear which proposal is a good one. The GOI proposal was, so when I say GOI, I'm referring to geometry of interaction. The GOI proposal was another compelling view because, Girard was able to make that work for, a situation that is remarkably close to quantum mechanics. So, he's got so there's something about the GOI view. There's something about the bigraphs view, but none of them have sort of come together into one framework. And this takes several steps to put them into one framework. Right? It allows us, essentially, the type system allows us to view a very wide range of models of computation categorically. That's another way of thinking about it. Cool. That's all I got. Any other questions or comments, or we can yield back to time? Awesome. Thank you so much, Arthur. I noticed you had joined us. It's nice to have you here. What prompted you to join us today?
I have time.
Oh, got it. Understood. Well, hopefully it was time well spent.
Oh, it's great. Thanks.
Yeah.
Cool. All right, folks. I will see some of you at the Dev Stand Up in a little bit. I'm gonna stop the recording now.